Good morning. This is my second time through this. I forgot to hit the record button at first, so we'll see how the second time goes. First time seemed good. Okay. So what we'd like to talk about today is two generalizations of Green's theorem to higher dimensions, and in particular, just to three space. So all of this will be in three space. And in all of these, we'll have a vector field F, which I will probably put in blue. So a vector field F, and this will map R3 to R3. It's a vector field in R3. So it assigns a vector to every point in three-dimensional space. And to look at this, you would use vector plot 3D. It plots the vector field, give you an idea of what the vector field is doing. Two of the things that we will want to compute here are the curl of F and the divergence of F. And the divergence of F is the trace of F prime. So we will need these two. These two played an important role in the two generalizations of Green's theorem. So let's look at the first one. The first one is called Stokes theorem. And let's set it up. It's in three dimensions. And it involves a surface. So we've got some surface. Let's maybe look at a parabolic surface here in three dimensions. And I'll call this surface S. I'll want this surface to be orientable, which means that there is a unique, you can define a unique normal vector at each point. Now, it would seem that it's obvious that you can always define a unique vector. I'm looking for a strip of paper here where I can show you this. But it's not true. There are surfaces where you cannot define a unique normal. And I will try to create one here. This was a surprise to mathematicians, but it is a simple surface. This surface is somewhat rectangular. If you bend it around into a cylinder, it has a uniquely defined normal. You can define an outer normal or an inner normal, but if you put a twist in it, this is called a Mobius band. If you put a twist in it and you try to define an outer normal, then if you follow this around, then when you get to the other side, that quote, uniquely defined outer normal, now it points in the opposite direction. So this is called a non-orientable surface, a non-orientable two-dimensional manifold. And Stokes' theorem doesn't work with this one. The bounding curve, there is a single bounding curve to this, by the way. This has a single bounding curve as well, but when you glue these together like this, now there are two bounding curves, a jaggedy one on top, one on the bottom. This has a unique bounding curve here. What we're talking about will not be meaningful on non-orientable surfaces. So we've got to have an orientable surface. We're going to call the bounding curve C. And I'll orient C so that the surface is to the left of C as I walk around the curve in that direction. So this is the situation. We'll look at the tangential, the line integral around C of f dot t. And this will be equal to, and let's get an idea of what it's going to be equal to by looking at Green's theorem. So I'll look at Green's theorem here in the plane, in the XY plane, but I'll draw it in three-dimensional space. So Green's theorem involves taking a region here, D, in three-dimensional space, in two-dimensional space. So this is supposed to lie in the XY plane. It's got a bounding curve here. The two-dimensional version of Green's theorem says that the integral of f dot t round C is equal to the double integral over d of q sub x minus p sub y. So this is Green at work. But q sub x minus p sub y, you will notice, is the third component of curl. So this is the curl of f dot the vertical, k. K is the vertical unit vector. And this gives you a hint as to what's going to be here. So this will be the integral over S. It'll be a flux integral of the curl of f. And the curl of f will be dotted with n. This is the flux integral of the curl. And this is Stokes' theorem. The line integral on the bounding curve is equal to the flux integral of the curl over the entire surface. And in the problems I'll give you, some of the problems will just say verify this. So it's to compute a flux integral, compute a line integral, see that they're equal. Another one might be the curl this is a more complicated formulation here. You need to parameterize the surface and so on. And you can shortcut that whole parameterization process of doing the surface integral by parameterizing a curve, which is generally easier. So, so sometimes these surface integrals are done using Stokes' theorem by just computing a line integral. So this is Stokes' theorem. And this is the first of the two generalizations of Green's theorem. So let's erase this and look at the second one. The second one, Stokes' theorem is a generalization to three dimensions, but it kind of ends there. There are Stokes-type theorems in higher dimensions, but they are different in some substantial ways. So this is kind of a climax theorem. On the other hand, what we're going to talk about next, the Gauss-Green theorem, holds in every dimension. And in three dimensions, it's called the divergence theorem. But it could be called a divergence theorem in all dimensions, because you will see because of the result. And this is a direct generalization of the idea of Green. So let's take a look. What is the setup here? Again, this is in three dimensions. And now we take a region, and I am drawing the boundary of this peanut-shaped region. But we are also interested in the inside of it. So I will call the inside region R. This is a simple region. I don't want it to have donut holes or Swiss cheese, just a solid region here. And this boundary of this will be oriented, and we're going to orient the boundary with the outer normal. So our outer normal the surface of R will be oriented by an outer normal. And we've got this vector field floating around here, so at every point there's a vector. And so now let's take a look at what we're going to do here. If we look at the integral over the surface S, of the flux integral. So this will be f dot n. We're going to change this to an integral over the inside, everything inside S, like Green's theorem changed a line integral to everything inside that line integral. And so this will be an triple integral over R. And we're again going to use the divergence of F. So this flux integral of F over the surface is equal to the integral of the divergence. Now the divergence is equal to the trace of F prime. So this is exactly what we got in the plane. So this formulation is precisely what we got in the plane, but in the plane, R is a two-dimensional region and S is its boundary, no longer a surface, but just a curve. So this is the Gauss-Green theorem. In higher dimensions, it works the same way. In n dimensions, if you take an n-dimensional region R and look at its surface F and S, and then F is a vector field on Rn, n-dimensional space, this is the theorem. Now there are some conditions here, both on F and on the surface. S has to be, for our formulation, S will be piecewise smooth, which means that it doesn't have to look like a peanut. It could look like, could have a flat part here. But then you would have to divide the surface into two pieces, bottom piece and the rest of the peanut. It could look like that solid piece of the paraboloid. And now the surface consists of the upper surface and the bottom. Now, those surfaces don't have unique tangent vectors at points of this curve here. So tangent plane to the surface and tangent plane to the bottom surface are different. And this is called piecewise differentiable. So that is the type of region and surface that we're talking about. And capital F needs to have some differentiability properties, so it can't be just continuous. Usual properties are that its derivative, F prime, is a continuous function. So continuous partials. So this is the Gauss-Green theorem or the divergence theorem. And again, I'll give you problems in the book where you verify that it's true by computing a triple integral, by computing a flux integral, showing they're the same. And also, again, these flux integrals can be difficult to compute because of the parameterization of S. So sometimes this is computed using this. And I think I gave you a couple problems like that too. So tomorrow we'll go over these two, talk about the problems. When you work the problems tomorrow, start with one from Stokes, move to one from divergence and sort of hopscotch back and forth between those. We'll take a look. On Friday, I'll give you problems involving 16.10. That's the summary of the chapter, just sort of a potpourri of what's in the chapter, line integrals, surface integrals, and so on. In any case, I will see you tomorrow in class.